And I'm gonna need a pen. Okay. So last time it came up in conversation about if you want to understand a particular function. How do you do that? How do you understand a particular function? Do you remember what we said? We were trying to understand left x. And so first and foremost, when you start to try to understand what a function is or does, what's the first thing we should do? Right. Yeah. Understand what exactly the independent variable is and the dependent variable. Right. So that's because that's basically what the function is. Right. It takes a certain value of a quantity and then spits back another value of a quantity. So we're going to do some of that today, but not in terms of like real world quantities, but just in terms of graphs, right? So we're just going to kind of be focusing on graphs. So in that case, when we think about what's the independent variable, what's the dependent variable, now we're asking based on what we see, right? Based on what we see, and what are the possible. So in R3, what are the possible independent and dependent quantities then, or variables? What would they be? The possibilities be? We're not talking about now. We're not talking about volume or temperature or mass or momentum or anything like that. We're just graphing in R3 in three-dimensional. So if I asked you, if I say here's a graph. So here's a function. F of c is c squared, and g of c is sine of 3c. Is c referring to like an axis? Is that what that's referring to? C referring to something in the graph? Is that what C refers to? No, C has nothing to do with the graph, right? So these function definitions are totally apart from their graphs. It's just defining a relationship between two quantities, and it's just using the symbol C as an independent variable. Okay? So now I've got a graph there, and I want you to tell me, based on functions f and g, and possible. That's a good spin there. So based on functions f and g and the coordinate axes in R3, what are you looking at there? What's being represented? I think Winston knows. An idea? What's being represented here? Given that I'm graphing something in R3 and I'm showing these two functions called f and g. Okay, can we do better than that? Maybe a little more definitive. Lydia, any idea? Okay, it's both of them graphed. What do you think, Veronica? Both functions f and g that you're looking at there? Just f. Why? Okay. All right, and so if it's a graph of f, is this the only way to graph function f in R3? Is this the only way you could do it? No. Okay, so there we want to be more specific then. I'm showing you the graph of f. Specifically, how am I showing you the graph of f in this coordinate system? Goes back to how do we understand a function? Or how do we understand this graph? By focusing on what? Independent, dependent variable, right? So what would they be? No, but now I'm talking about the graph now. So I'm talking, how is the graph utilizing the function f? That has nothing to do with c. C is right, like the chosen symbol for the independent variable. And I'm taking f and graphing it here, and how am I choosing to do that? Okay. So your independent is? What do you think? You agree with that? You agree with that? Yeah, that's yeah. So this is showing this blue graph in all its rotating glory is showing y as a function of x, right? So this function definition has nothing to do with graphing, nothing to do with x, y, z. But when I graph it like that, now I'm graphing y as a function of x. Does it make sense? And we recognize that because that's just our familiar what am I doing here? Oh, I'm probably still in this mode. There we go. Okay, so does that make sense so far? Come back. There it is. Okay, and we're going to pause it right here. There we go. Good. Okay, so now where's my x-axis? Yeah, so where's positive x? In what direction is positive x? To the right. To the right. And then what direction is positive y? So like back? Positive y is like back, right? Back. Yeah. Okay, cool. So here is this an xy or z coordinate? X coordinate. I'm going to call that x naught. Okay? And then I'm going to go here back to the corresponding point on the curve. How could I represent that vertical length? I want to represent that vertical length in as many ways as you can. How could you represent that? Vertical meaning, so we're in the horizontal plane, all right? So that length back into the screen, right? So x and y is like a vertical, horizontal plane, so not vertical this way, right? Okay, dy? Well, so dy is more like if we're doing calculus, we're doing intervals, and we're letting y increase through delta y intervals. That's more of the feel of dy. Okay, but it's a change in y, I think is what you're getting at there. So yeah, it's a change in y. And how could I represent that change in y? What symbols could I use to represent that length?
Would you do like f of x naught?
He wants f of x naught. Is it f of x naught?
By 0.
Subtracted by 0?
Oh wait. I mean that value on the
This length right here. So just as in concise terms as you can, represent that length right there.
Oh yeah, f of x.
You want f of x naught. Agree? Yep. Any other way to represent this? What's that, Alyssa? X naught squared, right? X naught squared, because that's what f of x is not. F of x naught is, right? It's x naught squared. Any other ways? Okay, so that's just a little warm up there. So let's erase. Any questions so far? Just getting accustomed to the function here. All right, I'm going to turn on another graph. We'll leave that one there. Yeah, that one. That's too fast. Just slightly, but just a little too fast. There we go. Slow but good. All right, so I want you to think about, what does this graph, does it show up as red? Yeah. What does the red, and let me make it a little smaller, that's a little too big there. There we go. Okay, so the question is, what does this graph represent? In other words, what does the red graph have to do with f, g, x, y, and z? I'm going to move it a little bit faster than that, okay? So okay.
So it's like in the XY plane, it's mapping f of x, but in the XZ plane, it's mapping the g of x.
Okay, so let's just talk about z here. So I should have done the last one. So z is an independent or dependent variable here. What do you think? Independent or dependent? Dependent of which function? They're both saying g. What the rest do you think? Z is a dependent variable of g. Because the z value is like the value of sine, right? Z value is like the value of sine. Okay, and so then what is the independent? What is the independent variable of g? So we're graphing function g here. What's the independent variable here? Y. So are we graphing the z coordinate of g, or sorry, we're graphing as a z coordinate the value of g for the independent variable of y on this graph. Yeah, so y so maybe we could say y from f is the independent variable of g. Do you agree with that? Do you agree with that? Okay, people on that. Good. Okay. All right. And now, how do we know that that independent variable for g is y and not x? How do we know that it's y and not x? So there's a big hint here. Stop. Gee, no, stop, not go. I'll put it back in there. What were you gonna say, Veronica? But how do we know for sure that this is z as a function of y and not z as a function of x? There's a big clue here.
I think how I see it is like that blue graph could be the axis. So the blue graph, since it's f of x, and since that's your independent variable that's acting right now is kind of our.
But the blue graph is made up of a series of ordered pairs, right? X and y, right? So how do you know for sure that the independent variable for the red graph is y and not x? So yeah, it's superimposed over the graph of f, but how do you know that it's still not based on the x values of that function rather than the y values of that function? There's a big clue. Can you just sketch sine of 3c without technology? Can you just sketch it? Can you sketch it on one of these fancy boards? Fancy boards on your table. On your marker.
Oh,
So everyone sketch here. More markers. Ready? Sketch sine 3c. Forget about what you saw on the screen and sketch sine 3c without the comma.
How like how long it would take to make a rotation? Usually it's like 2 pi, whatever.
Okay, you guys good. It's basically a transformation of sine, right?
Yeah.
So that, I mean, so just getting sine, just getting the right image of sine is going to be kind of enough here. And then you could talk about what the 3 does later. Because I don't have any axes, scale on the axes here. So those graphs look good. What about you guys? Okay. Keep going in both directions. Keep going in both directions. Okay, so now look at your graphs of sine or sine of 3c. Look at your graphs of sine, sine of 3c, and compare it to this red graph of g. G is the graph of sine 3c, right? So, see, do you notice anything? What do you notice? Okay, so it's a function, right? But comparing the red graph to your graph very carefully, it's kind of like those old games, right? Which one of these pictures is different than the others, right? You look at every detail. Look at every detail. Remember that highlights? Did you guys ever do highlights magazine?
Oh
Yeah.
Yeah. Okay. So, what do you notice anything about your graph versus this red graph?
like
Well, no, that's just the three-dimensional effect, right? See that's just it's getting skinnier just because of the perspective. Do you see?
Well, it doesn't like dip down at the origin.
Okay, what's going on at the origin? Is it the same at the origin? No. What's happening? The y values are always positive, and so therefore. Okay, so connect that to what you're seeing in the graph.
So y is always positive, so the value of the sine is never going to go below.
But it does go below. So you're on the right track. I mean, you got. What were you guys about to say over there? Did you have a thought? So what we're back to y. How do we know that it's y and not x? Any idea?
If it was X, wouldn't it be like flat? Like
If it were x, what would you see?
it would be graphed like on the 2-dimensional plane type of thing.
You could still graph it as a function of x along this blue curve. But then what would be different? It would go down at the left of the origin like your sine graph does, right? For these x values over here, it would come down and it would go down and up. But instead it does what? It goes back up. Why? So that's the thing. Why, right? So it's a little. Okay, but so we're again trying to answer the question. how do we know that the y is the independent variable and not x? So if it were x, it would look like sine at the origin. It would go through and be negative for negative x values. Why is it doing this? So it's doing something different.
Oh, because all the y values are squared in f. So like if you square it, can't be negative.
Can't be negative. So what is it doing as you go in the negative x direction? As you go in the negative x direction, it's graphing what? Like it were right? Like it were going to the right, right? So right. So that's what's telling you that our independent variable is y, because as we go this way, it doesn't come down the way the x being the independent variable would, but it's going back up. It's like graphing the sine function as if we were going a positive direction, right? And that's because the y values are positive. You see that? So what's going on here is how we know that the independent variable is y and not x. If it were x, it would come like this. It would look just the same, except here it would go down and then up and then down and then up like that. Okay. All right, so I want to see here, like this. Okay, and then I want to highlight this point right here. There's a point at the intersection of the blue and red graphs. So I want you to find, and we're going to call the x coordinate of that point x1. I want you to find that value. What's the value of x1? You kind of forgot this whole thing we just talked about. You've kind of just pushed aside this very important discussion we had a moment ago about this, right? Our whole discussion about this. Okay, so what do we know about the point x1, y1, z1? So how can we get started here? What's the key to getting x1? What do we know?
We know that z1 is 0.
He said z1 is 0. Agree with that? Yeah, right, because in the xy plane, right? So that's a good start. And what did we say? So values of z are from the function what? Values of z are from which function? G. Right? Okay. So we need to know what y value, because y was the independent variable of g, right? So what y value is going to give us the z value of 0? So that goes back to what graph? Sine graph, right? So am I looking for this point right here? Is that what I'm looking for? No. Why not?
Because, I mean, you went negative there.
Right.
You can't do that in the
So for the independent variable of g, what direction is this? For y? Right. So if we're doing z as a function of y, are we looking for this point? What point are we looking for? This one, right? Right? Because y is increasing here. That's why it goes up. That's the whole discussion we had before. That's why it goes up here. Because this is like the positive, this is, both directions are a positive independent variable because y is positive on both sides. All right, so in the sine graph, what point is that? If it's just sine, it's pi, right? If it's just sine, it's pi. But we need this to be pi, right? So we need this to be pi. Do you understand? When that thing is pi, that's when we get back to 0 for the first time. So what's y1? Pi over 3. Pi over 3 is going to make that argument pi. So what's x1? Square root of pi over 3. Okay, and he said, wouldn't it be negative? Is it negative or positive? Okay, I have one for positive, one for negative. What do the rest of you say? Positive or negative? Negative. Got two negatives, one positive. What do you think, Jason?
I would say, like, I could see why it could be positive because of the fact that, like, this sine graph like didn't start dipping down. But at the same time, I'd say negative wise because the position of that point is like left of that y-axis, so I'd say negative.
He goes with negative. What do you think? What's positive? What needs to be positive? The y, right? The fact that we think of y increasing in this direction, so this is positive y's. That's what makes this go up. But x is still a negative coordinate because it's like Jason said, it's to the left of the y-axis. So that's what Winston said, right? So negative pi over 3. Negative square root of pi over 3 is that x coordinate. Okay. Another question. So now, here, this point. So that has coordinates x2, y2, z2. So there's a vertical length from that point to the blue curve, agree? And then there's and then onto the x coordinate. So this is what? This is x2. This is x2 here. And then that's the point on the blue curve, and then straight up from there is our point x2, y2, z2. And so I want you to represent that length in as many ways as you can. Do you want to make it a competition? You guys done? You got all you can get? All right, then we'll have a face-off here. Who gets to go first? Flip coin. All right. Let's see. You guys can go first because you have less people on your team. Here we go. We're just gonna each are gonna say one until one team runs out, and that team loses.
So we should save our harder ones.
Okay.
Trying to snipe us in those.
Z2.
Z2.
Okay, yeah. Should I say we have that too, or what?
No, then you guys have to come up with a different one.
Oh, okay.
And whoever is first to run out, the other team wins. G of f of x2.
G of y2.
G of y2.
G of x2 squared.
G of x2 squared.
Sine of 3y2.
Sine of what?
3y2.
3y2. I don't think I have that one. Very good. What else?
Sine of 3 x2 squared.
Sine of 3 x2 squared. All right. More? Sine of 3. What was it? F of x2. You guys got another one?
I was trying to think of one on the fly.
Yeah, no, do it. Yeah, excellent. Yeah, totally. Can you think of one? How many is that? Let's see if I have any others. G of y2. G of f of x2 I have. G of x2 squared I have. Yep. I don't know, maybe that's it. Okay, very good. All right, so now I want you to notice something. So really, this red function is really about what? What is this red function really about? Now that we've come up, so I've picked an arbitrary point, and you've shown me ways to define what the value of the dependent variable of an arbitrary point on the red function. And what do you see going on here? What is this? Yeah, really, this is about composite functions, right? So I want to show you something. So this is really like a new function made from the others. So I can say, call it like h. So like h of x equals what? Z. If I said z was h of x, then what is the function h? G of f of x, right? And now we got another way to express this, right? Then this could also, this point could also, or this vertical length could also be expressed as h of x2, right? Okay, now keeping this in mind, right? Keeping this in mind right here. I want to show you some different views here. I'll get rid of this. So if I just show you the xy plane, what do you see? Just showing the xy plane, what do you see? Just f of x, right? Y is f of x, right? And if I show you the yz plane, now I'm backwards. No, I'm not. There we go. Now I'm showing you y to the right. No. No, this is xz. I want to show you, what do I want to show? YZ. YZ. No, this is that's right.
That is right.
X is coming out at us, right? Yeah, this is YZ. Sorry. All right, here's YZ. So we said y is a function of x, and what function is that? Equals. And so when I showed you just the xy plane, that's all you saw, right? And now I'm showing you what? I'm showing you the y z plane. And what do you see? G of y. It's all you see, right? Do you see anything to do with x there? No, you just see G of y, which is sine 3y. And then if I show you the xz plane, this way. This is the xz plane. What do you see? XY plane, YZ plane. I'm about to sneeze. Don't be alarmed. All right, in the XZ plane, I want to write something similar. What do you think? What's that? So tell me. So H, what? Do it the same way to these others up here. Z equals, she wants Z equals H of X. Do you agree with that? And what is that? What is Z equals H of X? No, we don't see, I just want a function of Z. So I just want a function that gives me Z given an X value. Sine of 3x squared. But we also know that Z is G of f of x. Where should I look to see that? So here I can look in the xz plane to see Z is, this is the graph of sine of 3x squared. So I can open up, watch, I can just open up a different, oh no. Oh no. Undo. What happened? All gone. Oh, so sad. So, let's write it out. Y is a function of x, and where did we see that? XY plane. And then what? Z is a function of y, right? That was G. And we saw that in the, and that was the same as sine of 3y, is that right? We saw that. YZ plane. And then Z, this one is, Z is H of X, right? And then we see that in the XZ plane. And that equals what? Sine of 3x squared. So let's see if it'll blow this again here. There we go. So if I were just to graph, watch. I'm just going to graph y equals 3 sine of 3x squared, just to see that graph. The same? Yeah. we also know that h of x is what? G of f of x. So how do I get to see that? So I can see z as h of x sine 3x squared in the xz plane. I can see z as g of y as sine 3y in the yz plane. And I can see y equals f of x in the xy plane. How can I see that? That h of x is g of f of x. What's that? How can I see that? I want to see all of it.
I'm just like see it. You should do like XYZ plane.
There's no xyz plane. There's the xy plane, xy plane, xz plane, yz plane. What's that? Region.
The space of X, Y, and Z will follow.
Yeah, so just like we've been looking at the whole time. So if you just backwards, there we go. I'm backwards. My mind is messed up. There we go. Okay. So kind of the view we've been looking at the whole time, where we see all three coordinates, right? So this view is the red graph. We're seeing GH as the composition of G and F, where you get to see the middleman, right? You get to see the middleman Y being the input variable, independent variable for the G function. But when you look at the XZ plane, you don't get to see that. You don't see Y as the middleman anymore, so all you see is sine of 3x squared. But now here you get to see the coordinate Y being the independent variable of G. So which one is the composition? What's the composition? Is it this? Is this the composition? Or is this the composition? So the function h of x or g of f of x? Which one is the composition? G of f of x? That's the composition? Okay. Any takers for h of x? Yes, so answer accordingly. Both, both. This one shows what? Shows the intermediate variable y in the process. And which view would we look at to see that? Not view, variable. And what view shows that version of the composition?
All three X's.
Yeah, like this isometric is called isometric view, where you see all three, like a three-dimensional view. And then what's the deal with this version of the composition? So how would you compare? How is this version of the composition sine of 3x squared h of x? How would you distinguish or qualify that version? What would you say? What's that version of the composition? Right. So then, in effect, what happens? Then, what does that do?
It's just the view of X.
Right. So it's kind of like the fast track version, right? Like it's like without it, kind of it eliminates the middleman, right? Eliminate the middleman. So it's like the fast track version. It takes you right from X to Z, and it kind of without the intermediary variable. So this is the That's the fast track version, right? Just takes an X, gives the corresponding Z, without any hoopla about Y. Both are the composition, right? One shows the whole process. The other just has the starting variable and the ending dependent variable result. Okay, so can you build this visual? What time is it? 1:06. Oh, I guess you can't yet because we'll come back and do it later because we haven't done parametric functions yet. Okay, so this today's one part of your project is going to be to do what's called rather than writing up lesson plans, you're going to be writing up something called a lesson logic. Have you done this in any of your other classes for Math Ed? Okay, so rather than lesson plans, you're going to write the lesson logic. So a lesson logic, a lesson plan is more about the details of what you're going to do in class. A lesson logic is less about those details and more about your reasoning for your progression of activity. So the reasoning for the activities that you choose. So the lesson logic, so what's the logic behind the way you're structuring the lesson, right? So includes the reasoning for making the choices you're making as a teacher and structuring the lesson as you do.
Does it still include like a sort of lesson plan as well, or is it only the reasoning?
So it doesn't have the level of detail about what you're going to do. So it kind of steps back into like segments out the lesson. You'll see. So you'll see. Because I'm going to indicate the reasoning behind the way lesson is structured and questions and activities chosen. So what you're going to do is before you create your own lesson logic for your project for your 3-day teaching module, you're going to analyze the lesson logic for what we just did. So I'll post this video and I'm going to post the lesson logic for our class today, for what we just did. And then you're going to go through and then you're going to read through the lesson logic and study it and then answer a series of questions about the logic, okay? This is so you can get a hang of what lesson logic is before you create your own. So this assignment due Tuesday is, again, it's you're getting your feet wet with what is this thing called a lesson logic, but I'm going to give you an example and have you analyze it, basically. And then when you get someone to the project, then you'll be creating your own. And I'm giving you a model, right? Just giving you a model and giving you a chance to think about what it's all about first. Make sense? Okay.